video will cover section 1.8, inverse function, and we're going to start by comparing two functions, function f and function g. And so function f says x minus 300, function g is x plus 300. And so what we're going to do first here is we're going to do function composition like we were doing on the previous section, 1.7. And so this is the same as saying f of g of x. We already know that is equivalent because the second function is the one that goes inside the other. So here what they're doing is just substituting g of x, and the function g of x has the equation x plus 300, so I'm going to substitute that g of x with that, x plus 300. And let's not forget there is a negative 300 here, so minus 300. And so if we do that, you guys know 300 and negative 300 are opposites of each other, so they add up to 0. So the result for that will be x. And we're going to do the same, but the other way. And so by doing the first one, we get the first condition satisfied, and you guys will see why in a minute. So if we do the other way, not f of g, but g of f, that will be function g inside function f. I'm sorry, function f inside function g, or g composed with f. So I'm going to substitute function f, which is x minus 300, and then after that, the x that we have here for function g is going to be replaced with x minus 300, and that will be x minus 300. And let's not forget there is a plus 300 that belongs to function g. And so negative 300 and 300 will cancel or add up to 0, and the result is x. So because of that, we could say that the second statement is true. And if both of those statements are true, if you get x equal to x after composing the functions, then you can say that one function is the inverse of the other, or the two functions are inverses of each other. In other words, one will undo the other. And if you guys know, if you've been taking classes with me for more than a year, you know that when we solve equations, I always ask you, what is the inverse operation of multiplication? What is the inverse operation of addition? And this is kind of like why I do it. Well, for other reasons too. Now, let's find the function value of this composition, so f composed with its inverse. And so for that, we're going to have f inverse of the function f of x. In this case, we're not talking about x, we're talking about 1300. Do you guys remember that problem from the previous section where the computer had a $300 discount? So that is similar to this one. It's actually exactly the same function. The inverse, what it's doing is just adding the 300 back. So it's like you're going to get the same price. So if we do function composition with inverse functions, the idea is that you should get the same that you started with. So if we start with x equals 1300, we're going to get 1300 also. So let's look at the table for function f. And if x is equal to 1300, that will be the input, so the output will be 1000. Now we move to the second table, which has the function inverse, and now the input is 1000, and the output will be 1300. And so, do you guys see? We get the same thing that we started with. And that happens because the two functions are inverses of each other. Now let's go to the next slide. And we did go over this a little bit last class. And we have here, let f and g be two functions such that if f composed of g is equal to x, and g composed with f is also equal to x. Also for every x in the domain of g and for every x in the domain of f. So if that is true, if you satisfy those two conditions, then you could say that one is the inverse of the other. The notation for that will be f inverse. It looks like it is an exponent, but it's not. It's just simply f inverse. So if we just change the name of function g to f inverse, if you compose a function with its inverse, you get x. And if you compose the inverse of a function with its function, you also get x. So that's what we have there. So let's go ahead and one interesting thing about those inverse functions is that they reflect across the line y equals x. We're going to see that in a minute. And remember last class, I think we ended the class by saying that is the identity function. Okay, so we're going to and you will have a question like this on the test. You are going to have to find the inverse of a function, and then after you're going to have to prove that they are inverses of each other. Okay, just so you know, no surprise. You will have a question like that. So here we're not going to find the inverse of f or g. We're just going to see if they are inverses of each other by doing function composition both ways. So f composed with g will be function f composed with g. So I'm going to replace g with this function, x minus 2 over 3. And so if we're trying to find f of that quantity of x minus 2 over 3, that means that we need to replace this x with everything that is inside the parentheses. So that will be 3 times all of this stuff here, x minus 2 over 3. And of course we add a 2. Now from here we know that when we multiply fractions, we multiply straight across, so that will be like multiplying 3 times x and then 3 times negative 2. I mean, you could do that, or you could just simply say this, the 3 here and the 3 here will equal to 1. So we may say they cancel. After that, we are left with x minus 2, what was the numerator here. And of course, we add a 2, and the result for that will be x, which is what we were looking for. So f composed with g is equal to x. That is true. So now we're going to do the next one, and that will be g composed with f. So function f is equal to 3x plus 2. And what that means is that we're going to replace 3x plus 2 for every x in g, and there's only one that is on the numerator. So we will have 3x plus 2 that is taking place of the x. We still have a minus 2 over 3. So after that, you can tell that 2 and minus 2 are opposites of each other, so they equal to 0. We are left with 3x over 3, and 3 divided by 3 is equal to 1, so you may say they cancel, and the final answer is x. So the second condition was satisfied. Now, when I ask you to show that on your test, you're going to have to show me the steps in between. If you don't do that, then you will more than likely not get credit for it. So what I mean is that you can't do something like this. So if you do that, I'm not going to give you credit. You need to show me why. Why did that happen? On the other side, if you do something like 3 over x minus 2 over 3 plus 2, and you just tell me that is equal to x, I'm not going to believe you. You need to show me step by step. Okay? If you are not sure, you can ask me during the test. Okay, so here we were just checking if one was the inverse of the other. So do you guys have any questions about that? Okay, so we're going to go to the next slide. Now we're going to find the inverse of a function. And so we used to do this in Algebra 2, and we had a list of steps. So step number 1, you replace f of x with y. The next step, step number 2, is you interchange x and y. And you do not change them to the opposite sign. You simply switch one with the other. And if x is positive and y is positive, then both will remain positive. What I mean is they both keep the sign that you started with. So we'll see some examples. And then the next step, step number 3, we're going to solve for y. Now, do you remember how we were verifying if a function was if an equation was the equation of a function? That was like back in section 1.1 or 2. And so we ended up, in some cases, we had to solve for y. And I don't know if you guys remember, we ended up with something that looked like this. Maybe not exactly the same. And so what I told you was like, for every x, how many y's will we have? 2, a positive and a negative. So this is an example of something that is not a function. So that's what step 3 refers to. If, after you solve for y, if the equation does not define a function, then you stop there. But if it does define a function, then that will be the inverse function. Or well, we could say that f has an inverse function. So if that is true, then you move to step 4, and step 4 just states that you replace y with the f inverse notation that we have here. And to verify your result, you will do function composition, like we did on the previous slide. And that is to verify your result. If you get the identity function, which is x, then you could, you will know for sure that yes, there are inverses of each other. Okay, so we're going to solve example 2. We're going to find the inverse of a function. And so we're going to follow the steps. Step number 1, we replace f of x with y. So y is equal to 7x minus 5. Okay, now step 2. We're going to interchange x and y. So the y will become x, and the x will become y. Yes, are we okay with that? Well, I'm not changing any signs. I'm not dividing by x or anything like that. I just switch them. Replace one with the other, or interchange. Now, step number 3, we're going to solve for y. And this y right here. So first, we need to take care of that negative 5, which we all know is subtracting from the y, correct? So if we take that across, or we do the inverse operation, that will be addition. So we will have x plus 5. And that is equal to 7y. Now here we know that y and 7 are multiplying each other, so we want to get rid of that 7, and the inverse operation of multiplication is division. So we're going to divide by 7. Now the question is, does that equation define y as a function of x?
Yes.
Yes, it does, right? If you pick any number for x, you will only get one and only one value for y. It's not something like the one I had here. So because of that, we can move on to step number 4. And step number 4 says just to replace y with the function notation f inverse. So f inverse of x is equal to x plus 5 over 7. Now, what type of function will this be? It is linear. It kind of looks like a fraction, but as long as the x is not in the denominator, it's still linear. It's not rational. If I was to ask you on the test, what is the slope of that function? What would you say? 1 over 7 or 1 7. What were you going to say? Sorry. 1 7, yes. If you're not so sure about it, you could always rewrite it by splitting the fraction. That means like 7 divides x, and 7 also divides 5. And we know that x over 7 is the same thing as 1/7 times x, and then we will have 5 over 7. Well, what is the y-intercept? Okay, and as a point? 0,57. Okay, now let's find the inverse of the next one. And again, we'll start with step 1. So we replace f of x with y. Step 2 was step 2. Interchange x and y. So x and y. Do you guys notice I'm not changing any signs? I simply interchanged x and y. That's it. That's all you do. Step number 3. Solve for y. So the plus 1, if I move it across, it will be subtracting. So x minus 1. And now we need to solve for y. How can we undo a cube? Cube root. And so we have to do that to both sides. The cube root and the cube will cancel each other or undo each other, right? Because they are inverse operations. And so now we have the cube root of x minus 1. Well, does that define y as a function of x? Yes, yes it does, because it is a root of an odd root. If we had a square root or a fourth root or a sixth root, then we could probably say no. Well, we will say no. But for that case, yes, it will still be a function. And I don't know if you guys remember from section 1.6 when we went over some of the parent functions, we had the cube. Let's say if I graph y equals x cubed, it looks like that. And if I was to graph y is equal to the cube root of x, it will look like that. Okay, so yes. If I was to perform the vertical line test to the graph in red, would it pass it? Yes. So yes, cube root functions are still functions. I mean, cube root relations are still functions. So because of that, we can move on to step number 4. And step number 4, for that, we replace y with f inverse. Now, does it matter that my f inverse is on the right side? It doesn't, because of the reflexive property here. So they do have the same meaning. Okay? All right, so let's move on to example number 4. We're going to find the inverse the same way. So step number 1, Gabriel, what do I need to do first?
y equals 5 over x plus 4.
Okay, very good. Step number 2, Genesis.
Interchange the x and the y.
Okay. Step number 3, Jose. Solve for y. Okay. And so first thing I'm going to do is take care of this plus 4. So inverse operation of addition is subtraction. So I will take this plus 4, move it across. That will be subtracting on the left side. So we have x minus 4, not minus 1, I'm sorry. So x minus 4 is equal to 5 over y. Now we still need to solve for y. What can I do?
Then you multiply.
Multiply what? Well, let's see what happens if I multiply by 5.
Yeah, 5x.
That will not really solve the problem.
You multiply 1 over 5.
That will just get rid of the 5. The problem is we need to get that y out of there, right? Okay. So what were you saying? Okay, let's think of this. What is the y doing down here? Dividing. So if I take this y to the other side, it's going to multiply. Now that we have done that, we know that the x minus 4, what is that doing to the y? Multiplying. So if I want to move it to the other side to isolate y, what will that be doing? Dividing, right? So x minus 4. What type of function is that? Rational. Very good. Because we have that x in the denominator. Right? So we cannot say it's linear. It is rational. If you were talking about transformations, what would that minus 4 be doing to the parent function? Horizontal shift. Very good, because it's affecting the x directly, right? Now, would it move it to the right or to the left? Right. To the right. Very good. Now, so does that define a function? Yes, it does, right? We even know the name of it. It's a rational function. So we move to step 4. And so step 4 states replace y with f inverse of x. And that's it. That is our answer. Okay. Yes. Sure. All right. So I'm gonna go. Any questions? Did you guys get a chance to copy everything? Okay. We'll give you a few minutes. I mean seconds. Yeah? You're good? Okay. All right. Okay. So we all remember the vertical line test, right? Yes? What do we use that for? To what?
To see if it's a function.
Okay, so to see if a graph represents a function. Very good. There's another test called the horizontal line test. And we use that to test for one-to-one functions. Now, if we have something say we have something like that. Would it be worth for me to spend time doing the horizontal line test? Why not, Viviani? You're correct. You are correct. Tell me why not.
Because the horizontal line test?
Uh-huh.
Because it's gonna like integrate twice, not once.
Well, you're thinking vertical.
Well, like if it, but horizontal, like if it was once and then twice again. I don't know if that makes sense.
Almost. Okay, Jose. Because it's not a function, right? So why would I even bother to test if it is a one-to-one function if it's not a function? Like Viviani is saying, it was going to touch 2 points, right? So vertical line test, it fails the test. So why would I even bother doing a horizontal line test, right? If it's not a function. I usually throw questions like that on the test, just so you know. And like everyone always spells that question. Yes.
So it has to pass the vertical line test before you can move to horizontal.
Correct. Yes. All right. So let's go ahead and graph f of x equals x squared. Let's do a quick table here. So let's take values from -3, -2, -1, 0, 1, 2, 3. Does that mean that those are the only x values? No, right? What is the domain for quadratics?
Negative infinity.
Okay, -infinity to positive infinity, or
All
real numbers. So if I want to find the function values or the y values, it will be 9, 4, 1, 0, 1, 4, and 9. So let's go ahead and plot those points. And so if we perform the vertical line test, is it going to pass it? Yes, it does, right? Anywhere in the function, it will. Now, let's try to find the inverse of that function by following the steps. So we start with the function f of x is equal to x squared, and then we replace f of x with y. Then we interchange x and y. I'm going to do that here. We interchange x and y, so we have x is equal to y squared. And then our third step is to solve for y. To solve for y, we will have to take the square root here and here. Now, since we just have x, we don't have a specific number, then we know that it will have 2 roots, a positive and a negative. Now, will that define y as a function of x? No, right? It will not. Now, what I want to do here is use some of the points that we have that are coming from our table. So we will use the point -2, 4, -1, 1. Let's use 1, 1, and let's use 2, 4. So now, for all those pairs, if we just interchange x and y, we will have something like 4, -2, 1, -1, 1, 1, and finally 4, 2. Now, if we were just looking at the set of points, you guys know how to identify if it is a function, right? Like, forget about the vertical line test for a minute. We know that as long as the x value is related to only one y value, that is a function, right? In other words, the x does not repeat. But if we look at the second one, after interchanging the x and y coordinates, would you guys say that that is a function? No. No, right? So we have 4 here, and we have 1 and 1. So because of that, this is not a function. So what the horizontal line test will tell you is if your function is a one-to-one function. So will this be a one-to-one function? No. So let's say not a one-to-one function. And so what we get from here is that if the function is not a one-to-one function, then the inverse, let's say its inverse, no, is not a function. It still has an inverse, but that inverse is not a function, okay? And if I was to graph this here, I'm going to try to make a small graph. If I was to graph this function here, it will be the positive square root of x. That will be here. And then the negative square root of x, that will be like the positive square root of x, but reflected across the x-axis, like that. So now, if we know that's the inverse, correct? So if we do a vertical line test on the inverse, it will obviously not pass it, correct? We'll touch 2 points. Of course, you don't need to do all this stuff because we have something called the horizontal line test, and that will tell you immediately that it will have, the inverse will be a function. Okay, so what I want you guys to do next is go ahead and test, and that's what we have here on this table, you know. I would like for you to test those. Are those functions? First of all, we need to establish that. They are, right? So they all pass the vertical line test. And so I want you to figure out if they are one-to-one functions. So, and if I ask you to do that on the test, please write the horizontal, draw a horizontal line test. Yes?
So for the test, it's like, do we have to find the inverse of it?
Yes. You will definitely have a question like that. Well, if it is a question that is only asking you to test if they're one-to-one functions, the horizontal line will be enough. If you have a question that says use this graph to reflect the points across the line y equals x, then yeah, you will have to draw the other one. But that's more like an Algebra 2 question. So no, I don't think I will ask you something like that. You okay? What section is this? 1.8? Okay. So horizontal lines, please. I want to see all of you tracing a horizontal line. All of you, please. I know you're very smart and you can do that in your head, but if you don't trace the horizontal line, then you're not going to get the points. And you're not going to like that. Okay, so which functions are one-to-one functions? Only A and D. That's it. Those are the only one-to-one functions. Okay, so let's write a little statement here. So we have graphs. Oh, and the answer was there. Great. All right, so we're going to write the following. A one-to-one function is a function in which no two different order pairs have the same second component. If you're looking at an order pair, x comma y, this is what they're talking about, the second component, right? How do we call the set of all second components? The range. Very good. So if we go back to that example of f of x equals x squared, we notice here how the second component is repeating, right? Yes? That also comes from the fact that it is symmetric with respect to the y-axis. So that's why the second components are repeating. So one-to-one functions are functions that no two different order pairs have the same second component. Let's see. Only one-to-one functions only one-to-one functions have inverse functions. And what I was saying before, any function could have an inverse, but not all of those are functions. Okay? Only one-to-one functions have inverses that are functions. Okay. Any questions so far? Anything that you would like me to repeat, clarify? Don't be shy. All right. So I like that. All right, next slide. Okay, so here we have that reflection that we were talking about across that line, y equals x, the identity function. And let me see what I want you to write there. Because inverse functions have order pairs with the coordinates interchange, if the point A, comma, B is on the graph of f, then the point B, comma, A see on the graph of F inverse. So the 2 points A comma B and B comma A are symmetric with respect to the oops, we need more room here. To the line y equals x. Thus, the graph of F inverse is a reflection of the graph of F about the line y equals x. As you can see on the picture here. So if we have that point A comma B, the inverse function is going to have the point B comma A. Remember how the steps to find the inverse of a function algebraically, I believe is the second step, we interchange x and y, right? Yes? Okay. And so what I want you guys to do now is to use that image to graph the inverse of that function. If you have a different color pencil, pen, marker, highlighter, whatever you want, you may use it. If you want to borrow one, let me know. Okay, so start by using, you could use the reference points 4, 2, 1, 0, and negative 3, 2. Remember, there's no need to change the signs, okay? You're only interchanging x and y. That's all you do.
If you give us a problem like that, do we have to like show that? Like, do we have to do that like the small little table kind of thing?
To be honest, I don't think I will give you a problem like that. That's too easy.
Okay.
I don't wanna like raise your hopes.
For the other one, either, right?
Huh?
For the, like, you know how we did one in the, like, before this one?
Yeah.
So, like, that one either? We want
On the
to
previous
do-
slide?
Yeah.
Let me
So
see.
that we can do it in our head.
Like this? Like
Yeah.
this? Well, that was just to demonstrate something, so that will not be a test question.
Okay. What else do you want us to do?
So after you do that with points, go ahead and graph it. So we'll have negative 2, negative 3, 0, negative 1, and 2, 4. I think I still have some of those drawings through. I think so.
So see, those are pretty cool.
I know.
Like there was like a diamond, and then somebody made Yoshi.
The diamond was perfect. That was like a perfect reflection. Not that I like diamonds, I really don't.
Yeah.
No, I don't wear any type of jewelry. Really excited. I don't know, since I was little. Okay, so graph it with, try to use a different color, please. Okay, and so it should look like something like that, and just for fun, let's go ahead and trace that y equals x line. You can see that they are reflected across that line, right? How do we call that line? What's that special name? What?
Identity function.
Identity function. And what was the multiplicative identity for real numbers? For example, if you have a number such as 5, and you multiply it by its multiplicative inverse, what would that be? 1/5. 1/5. And so we do that with the purpose of getting a 1. So that is the multiplicative identity. And I love talking about that because we use that in chapter 8 when we do matrices. My favorite thing to teach. Now, what is the additive identity? Oops.
Like 5? Wouldn't it be like 5 to this side?
Well, let's see if we have a 5 and I subtract 5. This is the additive inverse with the purpose to get 0. So the additive identity is 0 for all real numbers.
That's it will be for all real numbers?
Yes, correct. Okay, so let's go to the next slide. All right, now when a function is not a one-to-one, it doesn't matter that there's no hope, like you cannot find an inverse or you cannot find the inverse that is also a function. But we just need to do one little thing to it. And that will be, you guys see how half of it is blue, half of it is red? So we're going to just take one side of the function, okay? And this is very important in Pre-Cal 2, because we're going to look at the trigonometric functions, sine, cosine, and tangent, well, and the other 3, but more the first 3. So we will have sine, cosine, tangent, cosecant, secant, and cotangent. But we will also have sine inverse, cosine inverse, and tangent inverse. Those are the 3 that we use the most. Huh?
Should we write that?
No, I don't want to stress you with that. But it's a lot of fun. Okay, so just remember that, okay? When we restrict the domain, that will be very useful. Now, what I'm going to do here, we obviously know that if we do the horizontal line test, it's not going to pass it, correct? So we're going to have to restrict the domain. And actually, they're doing it for us already. So they want us to take all the x values that are greater than or equal to 0. So what we're going to take is this red part of the function. So let's go ahead and graph it here. Oh, I'm sorry, that is not the correct function. I think I made the same mistake last year. Do you guys notice we have a transformation? What type of transformation is that? Vertical shift, up or down? Down. So we start here. Then we have the point 1, 0. Then instead of having the point 2, 4, it will be 2, 3. And instead of having the point 3, 9, it's going to be 3, 8. like that.
What happened to it, like,
The other side we're not taking it because we are only using the function x squared minus 1 when x is greater than or equal to 0. So we just kind of ignore that left side. Now, if we do the horizontal line test here, it's going to pass it. Yes, right? We'll definitely pass it. So that means that we can actually find the inverse. Now, let's just write a list of points here. So we have the point, let's find it algebraically first. So first step, we turn this f of x into y. Second step, we interchange x and y. Third step, we solve for y, correct? So the -1, subtracting to the y, so we need to move it across or add 1. So that will be x plus 1 is equal to y squared. Now from here, to solve for y, we need to take the square root, correct? Yes? We know the square root will take care of the square because there are inverse operations. And now here, I know that we could say, well, when you take a square root and you have an x inside, you don't know if the x is positive, negative, so you could be talking about that plus minus situation. However, we are restricting the domain, so we're only going to consider the principal root, which is the positive root. So will that define y as a function of x? Yes. And so our step 4 will be to change the y with f inverse of x, and the equation will be the square root of x plus 1. If we are talking about transformations,
It's a horizontal.
okay, that's a horizontal shift to the left or to the right, not the left. To the left, okay. So the parent function of the square root functions, it goes like that, right? So if we shift the 1 unit to the left, it's going to be here, here, and there. So this function had the points 0, 0, 1, 1, 4, 2, and 9, 3. But since we're talking about a horizontal shift, 1 unit to the left, those points became -1, 0, right? We subtract, I'm trying to review for you guys. So we subtract 1 from every x. So this will be 0, 1. This one here will be 3, 2. And this one here will become 8, 3. Right? That's how I graphed it. Now let's look at the quadratic function with a restricted domain. And the points that I have here are 0, -1, 1, 0, 2, 3, I can't tell. Oh, and 3, 8. Yes, is that correct? Okay, so if we compare those two functions, are the points, I know it's kind of hard to see, especially if you're sitting in the back. So the points that I have listed here, are they the same as those but interchange, are they? Yes, they are, right? So that's what it is. All right, so now let's graph both together just for fun. And we'll take a break right after this section, okay? So that is the quadratic that we started with the restricted domain. And then I'm going to graph the inverse. And I have the points there for me. -1, 0, 0, -1. 3, 2, and 8, 3. I feel like I did something wrong. This point should be 0, 1, so up, right? Okay, so this is wrong. Thank you, Anna. So it was -1, 0, and then 0, +1, so it's supposed to be here. And again, just for fun, let's go ahead and trace the y equals x. So you can see they are reflections of each other, right? Okay, so this is the end of section 1.8. We're going to go take a break. And then when we come back, we will start section 1.9.